Okay, everyone, welcome back to the second part of the course. Uh, so I had a summer vacation. I did some work, but yeah, I hope that you guys had either good time, maybe whether you were working or took vacation. But anyways, the second half of the course is really more about how we're going to use LLMs for data management problems. So in the first part of the course, we covered really what was the kind of the fundamentals of LLMs and LRMs, large reasoning models. So now we're going to start thinking about how we can actually use them. So the thing we're going to cover today is this kind of topic of prompt engineering and vector databases and what's called RAG, retrieval augmented generation. So that's the topic of today. And as far as prompts go, so right, I mean, so the idea behind the prompt is, you have like the frozen LLM, and then yeah, you kind of concoct a prompt to kind of get the best you can out of it, and then you get some kind of response. Right. Okay. So this is frozen. So that's kind of shows like a snowflake. That means it's frozen. So this is not changed. This is what they call also a parametric model. You'll see people call it a parametric model because it's just a fixed set of parameters. Okay. So it's a big theta. Right. Okay. So we've covered this before, but there's the whole idea of a zero-shot prompt, which is just you basically come in, you ask a question raw. Yeah, there's nothing else kind of put into the prompt except for the question the user is posing. So then there's one shot where you show like an example of kind of what you want to see as an answer, and then you ask the question, and then you hope you get an answer of a similar form. And then there's a few shot, which basically means that you pack as many examples as possible into the prompt, and then you finalize it with the question you're going to ask. And few shot, of course, does better than one shot, and they do better than zero shot. So this is what's called the fact that these two better is what is sometimes called, and I think kind of a misnomer. It's called in context learning. Okay, but that's what you'll see it referred to as. Uh, so now dialogue itself, like a chat, that kind of is implicitly a few shot problem because the history of the chat is being used. We'll see this in 1 second here. And according to Bloomberg, of course, there was this quote that I saw a little while ago saying that prompt engineering can pay $300,000 per year. And I'm just, you see these things kind of at times, and you just kind of wonder what's the basis of that kind of claim. But I think it's good advertising to get people interested in LLMs because they think, wow, if I can just get good at crafting prompts, I'll get $300,000 a year. I don't think anything's ever that simple. But anyways, okay, so let's look at some code here. So let's just go over here and let's kind of nose into some code for chat. So let's just kind of see how this is kind of operating. It's being seen. Good. Okay. So what do we have here? So this is code, and in fact, this code is now available for you guys. If you go the recitation, I just made an announcement that recitation number 3 has been released. The initial part of recitation 3 has been released. So this code is in there. So what you see here, this is using LangChain for Olama. And what it's doing here then is that we have a prompt here, which is basically using this prompt template, which is coming in from LangChain prompts. And so what it is, it's just like it's like Python, right? So you have the interestingly, yeah. So you don't do this, you don't do that. That'll kind of screw things up, right? Yeah. So it's got its own kind of what is it? Like this kind of substitution. It'll come to me in a second. What this is called again? The substitution. It was basically on a famous library that did this kind of substitution method. But anyways, it's kind of copying that or using that. So basically, the idea here behind the prompt here is that we have two input variables of the prompt. We have the history and we have the utterance, and then they get substituted in Jenga. I think it's Jenga kind of standard substitutions. which is what Python inherited. But yeah, so basically it'll just like whatever the history is, whatever that variable history is, it'll get substituted in here, and then the utterance will get substituted in here. So this literally, once those substitutions happen, this is literally what's being passed into the frozen or parametric model, the frozen LLM. Okay. So, and then of course we set it here to, we're using OLLAMA. So I just set it to Llama 3.2 with a 0 temperature. And this is kind of a funny thing in Llama that they kind of exploit this OR evaluation to define these chains. I'm kind of against it, but it's what they do. So this is like this turn chain. So basically what it wants is it wants the prompt, which is this thing right here. So it's this prompt template that gets shoved into the LLM, and then that gets shoved into, that gets piped basically to the string output parser, which is coming in from LangChain as well. So it's a little bit of their extra kind of protocol that's kind of extended Python in some sense to kind of put these things, define these as kind of piped operations. This maximum history here, I'm going to ask you guys to actually play around with that a little bit. I just said 200 tokens is actually 200 characters. I'm sorry. This one's it being 200 characters. There's a little bit of a funny mismatch there between characters and tokens. It's not immediately obvious how you kind of rectify that. But in some sense, what this is doing is this curtailing. You'll see in a second here how this is going. So while true, it just basically says input. So type something in, and then if the utterance is quit, then we're going to break out of this. And then otherwise, we get the response, which is basically we invoke. The invoke is a special operation inside of Llama. I'm sorry, inside of LangChain that will basically kind of do this. So let's look at this for a second. What's really going on here? This is kind of what is a little bit bothersome to me. It equals that. There's this invoke. So it's like when these things concatenate together, what's happening is what LangChain is doing is when it concatenates or it uses this kind of OR operator or this pipe operator, I guess, what it does is it kind of prompt, which is from, it's a prompt template here coming in from LangChain. What this does is this has, like they've defined this operator here. So they're creating a larger and larger object. So what comes back here is an actual object out of LangChain. It's a LangChain type. And then that type or that class has the method invoke. And then you of course invoke it with the variables, the history and the utterance. And then basically it'll print the response because the response is going to plop out of the thing. Turn chain here, response. Let's see, where does response come from? The response is, yeah, so that's the result of the invoke. So it runs through the chain. So again, there's like hidden things going on here deep in the bowels of LangChain that yeah, I mean it's elegant, I'll say that, but it's a little bit kind of I would almost prefer just to kind of have a straight library. But anyways, right. So then the response comes out, and then what we do is we actually add the utterance, the question, or the comment, or whatever they were in the chat, plus the response, and that all gets packed into the history. And then we truncate the history here based on the max. We just take the last part of the history, the most recent part of the history. We take that, and that's all that we retain inside the history, and then we push it back through again. So this is just to kind of keep it so that the context, you don't exhaust the context window length with a longer and longer history. Okay, so I hope that's clear kind of how this thing operates. But it's very, very clear. It's very straightforward. So this is chat. This is chat. This is the chat interface. This is how a chatbot operates. Okay, now let's go back to let me stop the share here. Okay. And then I'm assuming that you guys now see the lecture slides, right? Could someone please say that in chat, confirm that you see the lecture slides now?
Yep.
Okay, good. Okay, so that was just the simplest version of using OLLAMA, simplest version of a chat interface we can come up with. But I wanted you guys to kind of think about something here. So this actually is the problem that you're going to get, and I don't know if you guys can read this here, but I'll read it out loud. This is the first problem on recitation 3. Okay, so the program chat has a pretty standard prompt. So that prompt, if you look at the prompt in the code, is just kind of like, you're an assistant for chatting with the user, blah, blah, blah. So what I want you guys to do is to extend the prompt so that the chat the chatbot exhibits a positive mental attitude, optimism about the future, and a fundamental belief in the goodness of human beings. So that is probably material that you're going to kind of put into the instructions on the prompt to remind the LLM to kind of behave that way. And then I also want you guys to do another one where you build a bot that is morose, suspicious, cynical, and that is keenly aware of the futility and meaninglessness of life. Okay, so the first one I'll call Nightingale after Earl Nightingale, this kind of motivational speaker, and the second one I'll name after Diogenes. So the issue here is basically the following: we're doing a little bit of prompt engineering here to kind of nudge the behavior based on the prompt. Okay, so experiment chatting with these two bots. Which one is more entertaining? Also, experiment with increasing the max history length. Does it help or whatever? So what this gets to, though, is this gets to kind of an interesting observation about prompts. So prompts really are kind of this magical way that you just kind of ask the L. You're almost like speaking to a person, really, or I'm not sure. You're speaking to something. You're not doing this in kind of a programmatic way. In some sense, you're kind of just hinting in the prompt, and you're trying to nudge a certain behavior out of the prompt. Okay. Now, chatbots, of course, can have, and they generally do have, quite complex and hidden prompts. So these prompts in the commercial chatbots, they really are kind of loading. There's a lot of stuff that they're not showing us in terms of what's being included in every time we present something to ChatGPT. There's a whole bunch of prompt material that also gets added into it, and that gives them a certain amount of power. And so then the question, of course, I just want to kind of pose, because I think it's kind of a timely question. When I say can they, that also means we, right? So I'm not pointing the finger. A lot of times when you point the finger at something, some they, it then has a funny way of turning it right around and pointing back to you. Okay, so I asked the question, can they or we, effectively work in advertisements? Okay, so in other words, could we use a chatbot to nudge the prompt, the hidden prompt to a chatbot? Could we use that to nudge the user toward buying a certain product or something like that? So the reason why that's important, of course, is that that advertisement might be the way to monetize ChatGPT, right? So ChatGPT, they are a company, right, and they're going to probably want to find out a way to monetize it. So the question is that can they work in advertisements, and then more importantly, can they have an advertisement market where they sell? Like if I'm a particular company and I say I want to buy, when things are kind of in a certain type of conversation, I would like to refer the user to my product, right? So I was using ChatGPT recently to kind of buy a tractor for my lawn, and it was an interesting experience. Now, I don't think they are doing an advertisement network yet, but it was kind of like, well, it's a funny story. I'm not going to get into it, but in the end, actually, it educated me quite a bit on the different alternatives. So it was better than Google. So I think that ultimately ChatGPT or maybe Google will come in and swoop in and take it, but I don't think so. Most likely because they're going to be cannibalizing their own ad network. Hard to say. And they're also under antitrust observation. So they have some type of, I'm not sure if they're under a full consent decree or something, but they are. Google's kind of hamstrung because they're big. So OpenAI might figure out a way to do that. And then, of course, generally speaking, can we work in propaganda or social control? So this is based on so maybe we probably would rather have a society run like kind of nudging people toward Earl Nightingale rather than Diogenes. Although Diogenes is pretty good. He's entertaining. So as far as entertaining goes, Diogenes is pretty entertaining. But then these are questions. I mean, so there's probably a lot of power in getting the ability to kind of like sneak your stuff into the chat prompt. And then also finally, can we use A/B testing or even something DSPY? I think this DSPY. We'll talk about this in a little bit. Is this way to optimize prompts? Can we use A/B testing or some kind of prompt optimization to converge on the perfect prompt? Okay, is there a way for us to test this? Maybe there's some very particular prompt strategy in here. Okay. I know that from our examples, like for somebody on recitation mentioned, it was kind of interesting. They said they got the supervised fine tuning that they got one of those concocted um, like under supervised fine tuning for recitation too. They found that if they put an extra space into their prompt, they got better behavior. So that's kind of like that might be something that would come up.
Now, okay, so now we're going to go on to something a little bit different. So we're going to talk about what's typically called semantic search. So you'll hear people use this term semantic search. So the way semantic search works is that there's a lot of applications to this, and we're going to show some here. But basically, what it is that you have a set of sentences or set of sentences that are attached to objects essentially. And these could be something kind of this could be rather small. So we could have like the number of different objects could be rather small. There could be something kind of like it's like a classification. So it may very well be that like, well, this classifies to this is like it's like I'm going to show later on this kind of call routing example of a car dealership where the different requests that users are making should be routed to either the garage or the sales department. So this could be like something like, okay, if it's something like, when will my car be ready? That could wind up being close to this object called garage question. Okay, this is like a question about the garage, whereas how much does such and such cost? That could be a sales. Okay, so we might have many of these sentences in here that map to different kind of classifications or objects here. And then when the user comes in and the user says, okay, when will my MFR be ready? Okay, so they've come in and the user has this question that they put in, that's the input sentence. And then the question is basically, well, all right, we want to map it to one of these responses, either a garage or sales or whatever. And so what we're going to do is we're going to basically just kind of compare it to all the sentence object pairs that are in our system. We're going to compare it to that, and then we're going to find the one that is the closest. So the one that's the most similar to this question here, for instance. So it might actually map into this one here, which would give us this object here. So this is semantic search. Like you have a set of sentences which are associated with something, and then you put in an input sentence and you find the nearest match, and then you get that something that it's associated with. Okay, so in an abstract level, that's what semantic search is about. Okay, so now if you think about it, we could already do this with just using BERT. And what we would do is we would just kind of encode these as problems of saying, okay, for the first sentence in the batch, we would basically say, okay, what is the semantic similarity, right? We'd have this SEP thing, and then we have the input sentence, the user sentence input, and then we would have this first sentence here, and then we could run that through BERT, run it through the transformer, and then have it compute. In these task-based specifications, if you recall, how the first GPT papers were doing that. We could put that in there. But this is completely infeasible because if we have like a lot of these things, we have like 10,000 questions in this system or 10,000 sentences in the system, and then we have an input sentence. We want to map to the nearest one. That would be 10,000 separate calls to BERT. And that would be just completely like a waste. I hope you guys see that. So just kind of like going directly to BERT and doing this, or directly to GPT and kind of doing it this way is not going to work out well in terms of performance. Right. So, well, then what do we do? Then what we do instead is we want to have what we really want to do is we want to do something. We want to calculate sentence embeddings. So what we want to do is we would like to take each of these sentences that are associated with objects and then compute for them and in a vector in embedding space, right? So this sentence right here asking about one particular car, or this sentence right here asking about how much something costs. Both of those sentences get turned into like these large vectors, which represent their meaning. And then when the user comes in and they have their question, right? Then the issue is basically, let's just kind of as a vector distance. So as a cosine distance problem, let's find out the sentence that's the closest mapping. So it might be, okay, this is the one that's the closest in terms of cosine distance. Okay, and then we would get this right here. So what that would do then is that would basically make it so that it just reduces it. We don't have to make a whole bunch of repeated calls to BERT or anything. We just kind of do this. We have all these kind of pre-compiled, these pre-calculated um, sentence embedding vectors, and then what we do is in the input sentence just matches which one does it match to the closes. And this actually, all in all, what this basically is, this is called a vector database, a vector database is what because these are all vectors, and then it computes the nearest one. Okay, so I hope that's clear. And then the question, of course, is that, well, that's nice. That's going to make things a lot, big, huge speed up compared to the other one, that other kind of obvious way of doing it. But the problem, of course, is that, well, how do we actually get the sentence embeddings? Okay, and it's a little bit more complicated because I mean, word embeddings or token embeddings are kind of simpler because we have a token and then basically we have, if you recall, GPT will give us, it will derive through the training, it will derive an embedding for a single token. Each token will have an embedding in that matrix. And that's all fine and good. So we have, if we have 512 dimensions for each, if that winds up being our D size or whatever. It's this if that winds up being how many different real values we have for each token in that huge vector, then all we have to do then is like there's a whole bunch of different distances we can do over it. Euclidean, right? That's the one that has a lot of square and then square root terms, Manhattan distance or dot product, or the cosine similarity. Okay, so the cosine similarity is very popular, and we'll consider that. And when we actually look at the embeddings that were calculated over the tokens, then it kind of has some kind of relationship to the meaning. Okay, so then, for instance, the two tokens, bad and awful, should actually be somewhat close to each other in this embedding space. Okay, and that doesn't help though with sentence embeddings because sentences we're talking about a sequence to a vector problem. So we have the sequence, which is a whole bunch of tokens, right? And each of those tokens might have an embedding vector. But how do we map that to a single fixed sized embedding that represents the meaning of the full sentence? Okay, so it's kind of surprisingly how bad this is right here, but this is what people were doing for a long time. Just about a little bit of the history here. There was this word to vec. So before transformers, was this word to vec work, which basically took a word and they computed the kind of or a token and computed it did pretty well of getting some kind of vector of the meanings, a vector that represents the meaning of the word. Okay, so that people were working with that a long time. And the naive way to do it is what you do is you simply take all the words in the sentence and you average them. So let's say each word or token. When I say word or token, I'm using it interchangeably. If you take each of those and they have 512 dimensions, what you could do is if I say man bites dog, I could take the embedding for man, the embedding for bites, and the embedding for dog, and just take the average of them, the average vector in 512 space. Okay, this is the average. But the problem is that we see this, and this is called the bag of words, because all that you're doing is representing a sentence by the bag of words. Well, that would mean that if you were doing that, then man bites dog would be equivalent. It would map to the same vector as dog bites man. And as we know, those have different meanings, kind of significantly different meanings. But still, this was kind of the initial kind of stab at it. Now, they had this, let's see if I put this right here. They had these STS corpora, which are these semantic distance of sentences corpora that was they were gathered by undergraduates, and it's a gold standard. This is a gold standard of distances between the semantic distance between sentences. The bag of words was the only thing they had up until 2017 when this InferSent system came along, which was a LSTM, which is a long short-term memory network, which is a recurrent neural network. That was a Siamese network, and I'll talk about that in a second, that was trained on text entailment. So he was using text entailment as its input to kind of to derive the distances or the inferred distance between sentences. It used a text entailment corpora to do the training. So basically, it was kind of like you take well, anyways, it's not so much so the detail of how they use that corpora to do the training is not so relevant. But this was the first system to actually beat bag of words on the gold standard. Okay, on the human judged gold standard. So that was a big deal because I was like, okay, finally there's some traction here beyond this kind of very naive way of doing it. Now, what people did, like when BERT first came out, what people started doing is they started saying, well, actually, it's like it's like here's a BERT network which basically encodes the sentence. And then there's the CLS, like the class input. And what we're going to do is we're just going to look at this either the beginning or we find actually somewhere in the BERT network, we find, and this has a 512, right? So this is the same dimension. We're going to just find one of these things. It doesn't have to do with like guessing what the next word is. But what we're doing is we're going to use that to kind of just like decide what the representation of the meaning of the sentence is. Okay, so that was just kind of arrived at empirically, but it wasn't very good. But still, people took that, and I'm not sure. I think it might have beat. Well, we'll see in a second how that compared. But it was like that people kind of hacked it, and they were using that for a while. But then along came SBERT, and SBERT was a real breakthrough. This is like real. This was really good. Okay, so let me just describe quickly what SBERT does. Okay, so what does SBERT do? So this during training, it does the following. It takes sentence A, so this might be like a sentence of John likes Susan, and this one, another sentence right here is John likes Susie, or this might be like, when will my car be ready? And this is at what time will my vehicle be done? Okay, so those are two independent. That's a probably good example. When will my vehicle be ready? When will my car be ready? At what time will this vehicle with this registration number be done? Okay, so those are closer. Those should be close in meaning, right? So what SBERT does is it takes BERT, the pre-training from BERT. So remember, the pre-training means that we went and we just ground down and we built this giant transformer network that over the whole web of information. So it's got like somehow baked into it is kind of the model of human language, right? That's what BERT gives us. So BERT takes forever, to generate. Maybe takes millions of dollars to get BERT built if it's over something as big as like GPT-3. It does that. It has those what SBERT has. It has those parameters. Right. And then it does a pooling. So what the pooling does, that simply says that this might be a 512 per token dimension. And what this does is this will then downsample. So what it'll do is it'll kind of do like a smoothing operation or an averaging operation. And let's say it'll turn that into something that's like, it'll take something coming out of BERT here, which is like the length of the context window, and it'll crunch it down into something that's maybe 2,500 or 2,448 dimensions. So it's bigger, but what it's doing is it's kind of summing over that. So it's not taking whatever the context window is times 512. Is downsampling. So it's doing some kind of sampling from it to kind of bring it into something that's a bit more. It's a much larger vector than the 512 for a single token, but still, it's fixed, and that's the number of parameters it is. So it just systematically will run like the first sentence through BERT, the second sentence through this BERT, and then whatever comes out, which is the size of which is the size of the context window times 512, it'll downsample that. It'll kind of crunch that down via averaging or smoothing into something that's 2,048 parameters. Okay. And that will give us the U and the V vectors corresponding to the sentence that came in here and the sentence that came in here. Now, here's what's important is then what we'll do is we'll take those two vectors and we'll do a cosine similarity. All right. And that will give it, if this was just, okay, this will give us something. It might actually give us something that's pretty close to what it should be. But let's say that we take those two sentences that I said before, and we want to then we're going to be basically doing something like similar to supervised fine tuning. We're going to wind up fine tuning Bert's weights so that that first sentence about the car, the sentence about the car should actually be very similar. Okay, so we have a 1 here. Let's say what it came out here, just because Bert has some kind of understanding here, it comes out with like, let's say a 0.67. I say, no, it should be 1. And that then is going to set up a loss that I'm going to propagate backward through these layers here. Now, the most critical thing to know here is this is a Siamese network. So when I propagate that, so there's a loss that was calculated here for that first sentence that's coming back here, and it's going to change the weights on the network here, right? And it's going to do the same thing with the other sentence. It's going to push back a loss. The important point is to say these are the same weights that are going to be affected when I do this. So these are shared weight. These are sharing the same weight. They're a Siamese copy of each other. So when I do a loss here, these are just virtual copies of one another. Okay, it's the same BERT network that's being trained on. That's the key insight is that you do that. Now, if you go and you train this over a whole set of corpus where you want to bring certain sentences into closer similarity, and you want other ones to diverge from similarity. You do this as a whole, as a process, and they use different corpuses to kind of do this training, and this is the essence. This is what SBERT is. This is SBERT. And then what we have over here is that, by golly, SBERT really kind of knocked it out of the park in terms of the semantic distances between sentences. I'm not sure if it's like human like equivalent. Like, so if you take people and you have this gold standard, and then you start asking people to kind of judge the gold standard, similar to what you're asking BERT. I'm not sure how people do if they do much better than SBERT does. Okay, so it was really a good result. So, and SBERT. I use SBERT in my system, so I'm really, really satisfied with SBERT. I think it's gone through a couple iterations in terms of like the same idea is there though, and we'll see some code that's doing it. It's using these nomic embeddings, but it's basically SBERT. Okay, right. Let's see here. So what are we doing for time here? All right, good. Okay, so let's get back. So now we have this. So now we've actually made some progress here. Let's see here. When we get back to, I gotta find this. Okay. So remember, we're doing a semantic search here. Now we have this SBERT system, so we can run things through. We can run all the sentences through SBERT to calculate the vectors that are like 2048 long, and right. And so now we have this full kind of technology to do that. So this gets embedded inside of a vector database. Okay, so these are vector databases. So okay, so assume we want to rank or cluster a set of sentences, paragraphs, documents based on similarity. Okay, that's kind of going back to semantic search. Okay, so basically what we do is we basically can do this calculation of k nearest neighbors over the existing vector database. Right. One thing to keep in mind, it's more advanced to have a persistent vector database. We just use a main memory vector database, main memory. So we just kind of build it and then we stuff it into main memory, and then we do our matches from there. Okay, we're going to look at some code here. We're going to know some code. So we have a Vector-DB, and then we have this fuse shot, which is something that kind of compared with. Okay, so good. So I think we're going to share the screen here. We're going to go over into looking at some code that does this vector database calculation. Yeah, I trust you guys can see this. And let's take a gander. I'm going to open the chat. Let's see. Right. Where did I put it? Uh-oh. Robin? Yeah, here it is. All right, here's the Vector-DB. La, da, da. Okay, yeah, it looks like a lot of things have changed here. I'm gonna have to go in and update those. Right, I'll do that after class today. Unfortunately, we can't run it then in real time. I don't want to do. Okay. So what do we have here then? How does it work? By the way, did anybody already? This is kind of further down in recitation. Did anybody already get this to work? Okay. Well,
No, I didn't try.
yeah, it's. I think. I mean, you might even want to wait for me because I just have to kind of figure out what the new name, what the new paths are to get to it. So, right. So let's see here. So how does it work? We have an embedding model here, and what it does. Now we have a vector store. So this is this. I should probably re-implement this at one point and just kind of like using either SQLite or PostgreSQL just so that we can make it persistent and also so that we can remove kind of dependence on things. So this is the k nearest neighbor. So this is k equals 6 here. So what it winds up doing is it takes the so it's using this kind of lang chain extra gobbledygook. Yeah, I would prefer to actually re-implement this so that I'm not using so I just kind of make it kind of more elementary. Anyways, the way it's doing it here is it's taking a set of documents here and it's going through and it is, let's see, it's right here, embeddings. So retriever, I guess it's all doing it there. So yeah, this is I should pick first. All right, so this is not so useful. Let's look at this. Okay, that's the actual input data. Okay, so these are kind of two examples, sales questions and garage questions. And this is something that's I'll talk about in a second here. So maybe I'll actually just kind of talk about this more verbally. And then it's important because we're kind of stretched for time here, so we'll stop the share then. So I'll have to fix that code, but what this winds up doing is it winds up taking those set of those dealership questions and it runs them through the vector store and it basically there's like I think 100 in total, so that gives us like 100 different points which are either associated with that's the sales maybe, and then here this might be garage questions. So we have, and they're probably going to be like more clustered over here, so if we're going to show it as kind of a space. So it kind of just indexes all those in this vector space, and then when we bring in like random questions that are not in the training set, but in the test set, and then we'd say like, okay, what are the most urgent repairs needed? When should I replace my car's battery? These are basically when we look at the closest this thing. If it's a garage question, this might come into here, and then the 1, 2, 3, 4 closest are all garage questions. So the inference is like almost 100% accuracy that it's going to find that it's going to classify this as a garage question. Yeah, so it's just showing that kind of thing, and this is kind of a practical example of using that. Now we can also do a few shot, which basically would be something like this: is that you would basically say. How much you basically provide a whole bunch of examples here, which are basically here's the classification, and then you basically ask, you finally come up and say, well, what is the then you have your input question. You say, okay, what should it infer to? So this is an LLM based method. The other one's a vector database method. And in recitation, you guys are going to compare those two approaches. Okay. So right. Okay. So let's see here. What do we have for time? Good. Good. Then we're in pretty good shape here. Okay, so what we talk about now is something called RAG, retrieval augmented generation. So this is a very, very widely used technique in LLMs. So the LLM limitations are, of course, hallucinations, outdated knowledge, and untraceable reasoning processes, etc. So what RAG does, retrieval augmented generation, is that it'll actually go out and bring in chunks of your actual private documents and then put them into the prompt that goes to the LLM. Uh, so I think this example here, this will kind of give us a real um, kind of intuition about this. So I like this actual, and I use this notation here of representing an LLM in the architecture diagrams as a snowflake. And that means that it's frozen. So remember, the LLM comes out of this giant pre-training process and then the alignment process after that. But the weight, it's a parametric model, which is what people will call it sometimes. But the weights, the parameters are fixed. So there's no when you get into the case of using the thing, you're just going to wind up relying on giving it the prompt, and then from that prompt it then generates a response. So in this example here, this is just showing kind of if you're not using RAG, kind of how this might work. So the example they were using in this paper was so the LLM was there was this big hubbub where Sam Altman was fired for a weekend. But the actual LLM here was trained before that. So the LLM had no idea. It had like a cutoff in terms of what current events. It's like if you add if an LLM was trained like last summer, you can't ask it about details about like what's going on in current events today, right? And that's the example that was shown here. So without RAG, what you do is you basically say, okay, how is this big question about Sam Altman and what happened in the 3 days that he was fired or whatever. And the without RAG, basically the response is, I am unable to provide comments on future events. Currently, I do not have any information regarding the dismissal and rehiring of OpenAI CEO. That's the kind of response you get out because it just sees this thing and says, well, I don't know anything about that. Okay, so the way RAG works is the following. We have a set. Here's the question that comes in. So how do you evaluate the fact that OpenAI, Sam Altman went through sudden dismissal by the board in just 3 days and then was rehired by the company, resembling a real-life version of Game of Thrones in the terms of power dynamics, blah, blah, blah. Okay, so this is the question that came in. This path here is kind of like not so great. This, however, is how RAG works. So what you do is you basically have a set of news documents. So this is like the current event news, or this might be your corporate your corporate documents, whatever it might be. A set of documents that come in here, and then what you do as a compilation phase of this whole thing is you wind up taking large chunks of that and putting it into a vector database, just like this like using SBIRT. You can use SBIRT or there's nomic embeddings to do that. So you chunk the documents, you break them down into like little paragraph-sized chunks. You calculate embeddings for those, and you index those in a vector database, right? Now, when the question comes along, what you do is you calculate what is the distance between this question and all these chunks, right? All these chunks that have been put into the vector database. You find that the nearest k of those, or the nearest 4 or 5 of those, and then you take those chunks and you actually bring those chunks into the actual prompt that's going to go into the LLM. So it might find, because it's looking at these documents, that Sam Altman's returns to OpenAI, blah, blah, blah. The drama continues. Sam Altman, blah, blah, see, undergo restructuring. Another chunk is that personal turmoil about OpenAI, blah, 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 who was lost. Okay, so it found these ones as very close chunks using vector database, using this kind of some sentence embeddings. It found these chunks, and it's including those chunks now. These are the relevant documents. It's going to include those chunks in what it submits to the LLM. So there might be a chunk right here that's talking about some shark attack in Hawaii, but that won't make it in because that's not anywhere close to this right here. Okay, so this is how you're kind of enriching the prompt with that. And then now you basically have the question and say, please answer the above questions based on the following information. And you include these chunks that you pulled in from the document database. Okay, and then you pass all that to the LLM, but now it will actually give you a kind of context-aware answer that's going to be based on the chunks that you passed in. Okay, so you're basically just enriching the prompt. It's kind of like a fancy way of doing prompt engineering or prompt augmentation, but you're just being really like you're indexing all like the documents that you think might be relevant to the questions the user are asking, like the current events ones here in this case, and you're organizing those in this big vector database. And then when the user's question comes in, you're taking their question and you're extending it with some of these chunks that you pull in from that database so that you're giving it a much broader, a larger prompt. And then it's a little bit magical, but then the LLM will actually give you back context, aware answers. It doesn't always work so well, but it's definitely a way that you handle this issue of not having up-to-date documents in the answers. So yeah, so RAG it's a great idea. Now the original RAG paper was much more advanced. It was actually doing fine tuning over the LLM. But in normal use now, what RAG means is that you simply have a frozen LLM, and that you're gonna augment the prompt so that you get better retrieval. Okay, so right, so this is just that described again. The user query, we have the documents, we have indexing the documents. Those combine, so we then go and we fetch out the relevant chunks of the document. We put that into retrieval. We then build this huge prompt and we send that to a frozen LLM, and then we get the output. This is naive RAG. And I think later on in the course, we're going to look at a little bit more advanced RAG. But as that kind of interplays with agents a little bit. So it might be a bit more modern just to talk in terms of agents. But that's kind of how it's going. So let's take a look here, because we have some RAG in the code here. We'll just kind of finish up with that and then take our break. Right. Okay. So let's share. Okay. I trust you guys can see this. Open the chat again. See, Zoom, you have to always open the chat. Okay. So here's what we have in terms of RAG. Okay. The first thing is I just wanted to make a mention of this. I'm using my own system that I built as kind of like a simple little RAG tester. So this is giving, like, I have all these HTML documents, right, for my system. And right, so it's going to go out and it's going to like pull in all those documents. And so that's just like the document. What do we have here? URLs. We have the URLs here. So this is just going to give us a whole set of URLs, and that's what actually this RAG is wind up using. So, how does this work? And then look at it again. This is pretty short, so let's just kind of go through it here. So the first thing it does is it goes out using those URLs, because it's getting the URLs here from the documents, and when it does the indexing, it is going to basically go and load all those URLs. So it's going to load all that literal text from those web pages. And then that's going to form this document list, which is document, which is just, okay. And then here's the important point right here, what it's going to do. This is kind of a naive way of doing it because there's no chunk overlap, but it's just going to literally split everything up in chunk sizes of 250 words, 250 tokens. Okay. It's going to actually in this case, it's words. So it's going to split those up. And then what it's going to do is it's going to then create a vector store where it's going to basically be doing this embeddings for each of those and then putting that out in a giant vector store. So what you're doing is you're associating the actual 250 word like pieces with their embeddings. Okay, and this right here is all fine and good. That's just like doing the indexing. And then what we basically say is you are an assistant following question and answering tasks. And what it does here is it will put in let's see here. So the utterance comes in, and then we have the documents. And then the documents wind up being the chunks that it will take the utterance, whatever you ask for your question, and this right here will return back the chunks that are the closest. Each of these are going to be 250 words. These are the chunks that are in those source documents that are closest in terms of embedding space to the question being asked. And it's going to then create the actual prompt that's going to go then into, in this case, Llama 3.1. All right. So that's the actual code. So you guys in recitation, you're going to develop your own little RAG system where you're going to point off at documents of your own interest and play around with this and see how well it does. So there's that.
More kind of advanced techniques in RAG. So what you'll see is you'll see this kind of like this paper that I'll be posting on the website. It's kind of a, I hope they have a new version of the paper because they've gone through a couple of versions of it where they've been refining it. It's very encyclopedic. It kind of goes, it's really a laundry list of all the different RAG type techniques. But basically, there's this whole issue then of doing things more, kind of introducing more steps in here. That sucks. Wish that didn't happen. I'll have to find out what was I saying there. Query expansion. Yeah, my printer. Okay, I'll have to kind of look at that in a second. So in the indexing side, okay, so we could have a sliding window rather than just breaking the chunks literally on like a 250 boundary. We could actually have it so that yeah, we have like here are our documents. So we have text in the document, and here's one chunk, here's another chunk, here's another chunk, so that we don't have any weird artifact about, so we're always kind of displacing. We're doing half pieces all the way through, so that we don't have any kind of abrupt ending to the we don't have any kind of strange artifact because of the boundary of the chunk. So that basically doubles the number of chunks over a set of documents, right? If we have a document and we have chunk size 250, and then we run it over and we get 100. Now, if we do it with sliding here, or we do it with overlapping, we'll get 200 chunks. And there's a lot of other like tricks to doing that. So a lot of like what people will pack into these systems is like maybe some special domain kind of preparation or some pre-processing that will kind of do things. Now, there's an interesting technique called Raptor, which actually it's not so complicated. I mean, it's just you just kind of think of it this way. What it does is the following. Here's our original document. And what Raptor does, let's just do a naive Raptor. This is one chunk. Here's another chunk. Here's another chunk. Then what we do is we ask an LLM to form a summary chunk of these two chunks. So now we actually say summary. So we take these two chunks here and we put them into an LLM and we say summarize them in so many words, the size of the chunk size. And then we actually have this abstraction, this abstract chunk, and we do the same thing over here. And if this is like a power of 2, what happens? And then we have a summary here of these two chunks, and then we can actually ask the LLM to calculate yet another summary of these two chunks here, the summaries of the summaries, right? And we can just kind of build this thing recursively up to the root, where we're going to have some chunk that summarizes the entire document. Okay. So the idea behind Raptor is if you actually organize your chunking based on Raptor, then inside of the vector database, you have things at various levels of abstraction. So if people ask a question at a little bit higher level of abstraction, maybe that is best captured by one of the summaries in the tree going up. Okay, so this Raptor is kind of a nice, clean, simple technique that allows you to get a little bit more out of these. Now, of course, the cost that you incur is you have to make a whole bunch of LLM calls in the compilation of Raptor process. Okay, but it's a good kind of clean technique. And in fact, I'll ask you guys to implement that in your recitation 3. Query routing. Okay, so it doesn't really show up here in this right here, but we might have multiple systems. So I have one system that deals with gemstone questions. I have another one that deals with NFL questions. I have another one that deals with Formula One. In comes the user's question, and what we might want to do is we might want to do some routing. So we say we have some kind of descriptions of those data sources, and we say which of these sources best answers the user's question, and the question being this, and the source descriptions being this. And then the LLM will give us an answer to that, and then based on that, we will route it to a specific processor. We'll route it to a specific for specific handling out of a specific tool. Okay. Now the simple version of that is that you're just doing routing where you're picking one path through the system, right? You go one path. You basically say, okay, we have like several different sources here, and I say, oh, this is the best source, and then we're going to go to this source, and then we might go to some other source here, and then it's going to complete, right? What we'll see later is that in more advanced versions, you actually go to both of them and then you do a fusion process where you try to fuse the answers back together again. Okay, so it can get quite complicated. Now, query rewriting. So there's this issue of pre-retrieval. So this is this issue of kind of what we do to kind of like in the indexing right here, rather. What do we do to kind of get better indexing? Raptor is like an example way. Another one that's interesting is what we want to do is we want to align the user's question better to the retriever. We want to align them better to the retriever. So actually, in the case of this, um, uh, we have this notion, what's called hide. It's also another real simple thing right here. And what that basically, what hide does is it says the user comes in with a question. So the user comes in with a question, what are McDonald's top selling items? Okay. Now that is maybe not going to match the database so well because the database is talking about burgers, fries, milkshakes, hash browns, which regrettably McDonald's, at least in Umeo, McDonald's, they discontinued the hash browns, which is really the only reason I went there, unfortunately. So, because I guess it was costing too much, but they had lovely hash browns before they discontinued. But oh well, that's life. By the way, have you guys seen The Founder on the term of McDonald's? It's a good film. I recommend that film. I just watched that film recently. Um, uh, so if you say this, you ask the LLM, okay, I could say, I could ask the question of like, hypothetically, what would a good answer to what are the McDonald's top selling items be? Okay. Hypothetically, what is a good answer to the following question? That's our prompt template is hypothetically, what is a good answer to the following, and then to the question, and then what are the McDonald's top selling items? Okay. Now it's not going to maybe get it right, but it's going to be talking about burgers and fries, and it's going to be talking about tangible things. It's probably going to get that out of it. It probably will get that out of it. And then if you take that and use that, that thing that's more specific, it's kind of gone down to the details. You use that to actually do the retrieval over the vector database to find the closest chunks to that. You'll actually be bringing in like relevant chunks as opposed to if you put in just this abstract question. Okay, so just empirically, it's been shown that hide, which is a very simple technique, hide will improve in certain domains. Hide will improve your answers. Okay, hypothetical document embeddings. Okay, now the cost, of course, is you're making an additional call to the LLM, right? Because you have to kind of generate the hypothetical document that would be the answer. One sec here. I just want to see what one sec. Right. Lecture 7. This is slide advanced. I just want to see what I skipped here and what I'm missing here. If there's something relevant to talk about here. Oh, I see what happened. Oh, that sucks. Free expansion better. Man, that really bugs. One sec. Better. Okay, I think I'm just going to do it from memory here. Query expansion. So the idea behind this is almost like our chain of thought kind of stuff we were talking about before. So it's kind of like saying, we take the question and we say, oh, could you break that down step by step? And that will generate a whole set of fresh questions that are more detailed. Or the user's question comes in and we say, oh, well, we send this to the LM. This is the prompt template. Please break this question down into multiple questions or some such like that. And if I ask a question like, how do I make an omelet? It'll then basically break that down into multiple questions, and then I'll treat each of those as a separate RAG problem. Now, that example of the omelet thing probably won't work so well. But what this is essentially this query expansion or chain of thought, or this kind of like expanding it out to multiple questions. This is kind of like what I would say is kind of like I hate to use that expression. It's kind of anyways, I'm not going to use the expression. It's kind of like the El Cheapo way of doing reasoning. Okay, it's reasoning for people who don't have, we're just doing this on our own laptop or something. So we can maybe start experimenting with some of the reasoning or the chain of thought stuff inside of like kind of doing kind of the question query expansion. So you're taking the question and you're expanding it to multiple questions. Okay, that's all. This is all pre-retrieval. Then the post-retrieval stuff is what's going on here. And then you can basically say something like this, like you say, okay, when we get our chunks back, what we want is we want to put the most important material. So if we have a ranking, let's say that we got the chunks back and we have a ranking. And naturally, we would have a ranking, right? If I say the n nearest neighbors, there's a natural ranking there, the closest, the next closest, etc. So what we might want to do is we might want to put the material um, of the more important chunks further, like either at the beginning or at the end. Because what's been observed is we have this thing called the lost in the middle problem. So when you have a very large prompt, it tends, pardon me, it tends to be that the material that's in the middle, it has the least impact. So there's this whole issue of doing some re-ranking to kind of get better results. Then there's a whole question of like doing maybe some compression of the chunks, like maybe like removing some of the fluff or redundancy in the collection of chunks. And then also we might, if we have multiple retrievers that we're all engaging, then we have the whole question of fusing answers back together again. And people have come up with some different ways to kind of they call it like the normal RAG. Let's say I don't have that. Okay. Well, they call it like rewrite, retrieve, re-rank, and read. So yeah, framework. So there's some different names going on. It's hard to say kind of what's going to happen with all this. This is very much a jungle. The whole RAG thing is much more of a jungle. So, and it becomes even more jungle when you go into what's called modular RAG, which is really just kind of like saying, oh, well, you can kind of engage these things in some other alternative architecture, which kind of plans out all the different kind of operations you're doing over the LLMs, et cetera. So this kind of can get arbitrarily complicated, but one of the things might be like doing database access, web search. So yeah, so like, there's a whole question of agents, and we're going to have a dedicated lecture on agents next week, where we're going to talk some of these things about some of the actions like web search, or agents are a little bit different, but you might want to go off and do web search. So all of these things are, you might have a memory that you're kind of maintaining, an episodic memory that you're maintaining. There's the routing, the fusion stuff. So there's just a lot of, so it's, so we're aiming at a more adaptability and versatility. It's not necessarily just a straight chain. And again, inside of that, we have lots of other kind of like ideas about kind of building these kind of big RAG systems. Like, right. I mean, there's like, it kind of almost becomes kind of programming language complete in terms of how people could potentially do this. And then, of course, we talk about fine tuning. So the fine tuning stuff comes back from the original RAG paper, and we might want to talk about doing some fine tuning over kind of some kind of like custom LLMs that are inside of our RAG pipeline. This is really interesting. I'm not sure how much has been. It was an interesting idea. I'm not really sure how far it's gotten. It seems like it's kind of been discarded. I'm not sure how much work is going on in this, but there's this idea of doing kind of optimization of the prompts. So having a system that does kind of prompt optimization. Of course, you need to have a way to score what's coming out of these RAG systems. That's always the key is you need a way to score it, so that you can then feedback something to kind of guide the optimization. And then of course then comes down to this whole kind of holy grail, which is this kind of potential of end-to-end training. So if you think about it at one level, a lot of that reasoning stuff that we talked about, the large reasoning models, a lot of that is almost, but it's not really RAG because it's still kind of doing it over a fixed set. So yeah, I mean, there's a whole bunch of things going on here. So basically, you have I'll make a mention of this right here, but like the two camps or the two types of people, the two types of efforts. So let's just talk about some of the things coming up here, or like some of the things that might kind of like impact all this, impact RAG. There's a quite inane debate that's going on the net right now about whether or not long context language models are going to kill RAG. Because the idea behind it might be like, oh, who needs to use RAG anymore? All we do, since the context since the context window is so large, we just pack in all the relevant documents inside the context window and then ask our question. Why do we need to dick around with chunking and all this other stuff with RAG? Why do we need to do that? So okay. I honestly am on the side that says you need RAG. That you don't want to do it that it won't work ultimately to do it that way. Now, why can we have long context windows? So there are two principal techniques. There's something called landmark attention and ring attention. I'm not going to go into the details of these. But what they're essentially doing is they're basically having, you know, the big attention matrix that we had, right? Especially with causal attention, where we had like all these interactions right here. And this is the size, sorry, this is the size of the context window right here. Okay, well, if we do all the interactions, if every word can talk to every other word, then what this winds up being is this winds up being on the order of n squared interactions in attention. But what these things about landmark and ring attention, which are kind of like allowing, so like the idea that if you look at Moby Dick, I mean, call me Ishmael, call call me Ishmael. Okay, we have me in the call me Ishmael, and then we have some word that's way out in deep into Moby Dick about like them drinking like rum and some kind of port or something. That me and that rum that's 50 pages into Moby Dick, those should really be talking to each other in an attention mechanism. Okay, things that are close by should talk to one another in an attention mechanism. Okay, and then what ring attention does, it does a little bit of abstraction there. So ring attention is a little bit, landmark is a little more naive, ring is a little bit more deep, but that's kind of the idea. They're basically, from an algorithmic point of view, is they're turning something that's n squared into something that's on. All right, that's kind of the point behind it, and that's why you can get super long context windows. All right, now my question is this: will this exacerbate lost in the middle? My intuition tells me this is not going. This feels a little gimmicky. I don't think so. I maybe ring attention, maybe, but it's like they're doing some kind of compression. This is lossy. Whatever they're doing, it is lossy. So what's going to happen? And then the question is this going to exacerbate lost in the middle? But there's a whole bunch of people who are basically saying, well, what they're basically saying is they're saying that, well, this is going to kill RAG. And then between the lines, what they're saying, and I think it's a kind of a demoralizing message, and I don't think it's a correct message. They're saying, listen, Pee-wee, that is you, little small timer, and they're talking to me. You don't have any business really kind of doing anything fundamental in LLMs. It's the big boys, like the big, foundational models with their giganto resources who can have these super duper long context models. They're going to eat your lunch. They're going to beat you. So why don't you just give up and not try? And that's called building a moat. So I'm instinctively kind of thinking, what's in their interest economically? So I know that's a fallacy to kind of point at people's interest, like when they say stuff and to point at their interest, but it kind of, my intuition says that that they want to they don't want small timers to actually take a crack at problems. They want to have it so that we all kind of bow down before the giganto models. So I don't think it'll kill it, but anyways, because RAG is a lot less of a black box, so we actually have control. So us small timers have a chance to get in there and kind of fiddle with the thing and kind of work it, and then use our ingenuity to try to solve things. It's faster and cheaper, especially if you have Olama going, because you can run it all locally. And yeah, and then okay, like small timers like me, I can innovate RAG techniques. But let's just kind of let's give the devil its due, I guess. Behold GPT-5. Okay, and by the way, I don't know if you guys heard, but the rumor is that GPT-5 is going to release this month. And the big question right now is OpenAI going to declare that AGI? Are they going to declare it AGI for contractual reasons with their enemy, frenemy, whatever, Microsoft? So God only knows, but this is going to be quite a page. This is going to be interesting to watch, the whole thing. But presumably GPT-5 is releasing this month. And it's rumored to have a giganto context window. So over 1 million tokens. So maybe the big guys are going to win. So we'll see. But it'll be very interesting to kind of watch the developments. Watch the developments this month, in fact. So we got a front seat here. So okay, guys, that is lecture for today.